Hello, my name is Austin, and I'm going to be doing part 3 for the Fundamentals of Aero ANSYS project. This is going to be the flow simulation around a stationary cylinder that is 2D. So first step, we're going to bring the fluent piece over like we did in step 2. Right click on this and do new design model or geometry. Wait for that to open. So with this one, it's supposed to be a 1 meter circle. So let's put that circle in there. First, let's select the Z. We're gonna put this circle in there. And then we're also gonna put a rectangle. I'm gonna put this one out in space too, because we want the whole region for the mesh. So for the diameter, like I was saying, it's gonna be 1 meter. Then we're also gonna have to do a vertical one to here. To make that good, we're gonna need a vertical one from here to here. To make that the right size, we're going to need a horizontal one for here to here. And then we're also going to need one from, from here to here. Perfect. Okay, so dimension 1, we want 1 meter. I'm going to do a 50 by 50 block. So for H4, we're going to do 50. And then for H5, we're going to do 25, which should center it. And then for V2, we're also going to do 25. And then for V3, we're going to do 50. So we now have our 50 by 50 piece. We're going to go to concepts. We're going to go to sketch from surfaces. We're going to select the sketch. We're going to click apply. We're going to click generate. We now have our area with our opening in the center. Perfect. We're going to save this. Let's save this project. We're going to save this as art. Perfect. Let that save. And then we are going to open up the mesh. So with this mesh, we just want to make sure we're getting it fine enough that we get to see this wake region. Because we're doing an inviscid case, a viscous laminar case, and a viscous turbulent case. So let's put this here. So to do that, I'm going to first insert a method because we want it to be triangular mesh. So we're going to click OK here. We're going to change this to triangles. Perfect. We're then going to insert a sizing constraint, and that is going to go on the actual circle. So let me actually, I selected the wrong thing here. Let me unselect real fast and select the edge. We want the edge, not the body. Perfect. And then we want the element size. We want number of divisions instead. We want no for capture curvature. We want it to be hard. Okay, and then for the number of divisions, I'm going to do 200. So that's perfect. There you go, edge sizing. And then I'm also going to insert a inflation here. And then for my boundary, I'm going to select the edge there. And then with this one, we're not going to do a smooth transition. We're going to do the first layer thickness. And I want the first layer thickness to be that. And then we're going to do 100 layers. I think 100 layers should do good. That should give us a pretty big or pretty fine mesh, sorry. So we got that. And we're going to change this mesh set from 353 because I'll show you right now. If I generate this, so you can see here it's very fine here, but then here it's freaking huge. We don't want that big of a mesh. So we're going to change this to 12. And we are going to remesh this. We're going to click update. And it's going to take a second. The more RAM you have, the quicker it'll be to mesh. I only have 32 gigs, so it's going to take a second to mesh this. Thing. Essentially, we're looking for a finer amount outside in this region because that center region was already meshed pretty good. We're looking for, on my previous runs, I was getting somewhere around 300 something thousand elements and 100 and something thousand nodes. Of course, it all depends on the size of your shape and what you're actually looking for. This mesh. Oh, and the mesh statistics are going to show up down here. So this is where you get to see your elements and nodes. Yes, wait for this to finish. There we go. Perfect. All right. That is exactly what we're looking for. Exactly what I was saying, 300 something thousand, just shy of 200,000 nodes. You want it to look black when you're this far out. Because that's meaning for this case, you're fine enough of a mesh. Now we're also going to name these. So we're going to name this as inlet. We're going to name this one as outlet. And then we're going to name these actually together, the control select. I'm going to call this symmetry. And then we're going to name this guy right here wall. Perfect. So now we've got all of our name selections. We got our mesh. We got our triangle method, the edge size, and the inflation. This is good. So we're going to save this. I would recommend you save on each step. So it should be good now. And then we're going to go back here. We're going to update the mesh. Definitely want to make sure you update the mesh. For here, you want to click double precision. And depending on the amount of CPU cores your CPU has, I have 6. So I'm going to put 6. You put 1, it could just take a long time. I would suggest putting to the maximum of your PC. But once this is open, we're doing the inviscid case first. So I'm going to do the inviscid case. And once I'm done with that, I'll show you how to connect the mesh so you don't have to redo the geometry on the viscous laminar and the viscous turbulent case, because that's just annoying having to redo it all. All right, let this load up. Cool. So first things first, we got to change this off. K omega, and we're going to do inviscid. Perfect. Then we're going to go to our materials and air. I'm doing 1 as my density. Make sure it changed, make sure it updated. Cool. Then I'm going to go to my boundary conditions inlet. So in the assignment, it says 5 meters per second. So I'm going to do 5 meters per second. Perfect. So I have that. I have my density. I have that. So we're also another hint. This thing called reference values here, it didn't change. So I want to make sure you update this or results will be kind of wonky. So we have that. We have that. Oh, methods. So we're going to go here. We're going to change this to simple. We're going to change this one to presto. Not really sure what that does, but from everything I've seen, it makes it solve a lot faster. So with that, then I'm going to go to my residual, which is under monitors. And we're going to change our residual to 10 to the negative 6. So I'm going to add 3 zeros. Click OK. And then I'm going to check it. And the residual is perfect. Okay, so we have our residuals. Now it's time to calculate. So I'm going to click Run Calculation. I'm going to put 1,000 iterations. I know it's not going to take 1,000, but I just put that. It's going to start running, and then you're going to see this graph pop up with the iterations. 10 to the negative 6. With this one, I believe it like goes straight, and then it finally curves off at the end. This one's going to take a second. Especially, this is where it'll really hurt you if you only put 1 CPU, 1 processor, because this iteration stuff is very CPU heavy. It doesn't really matter about your GPU. So yeah, this one's going to be flat, and then it'll finally at the end curve. I forget it, what iteration count. But we're just going to let that run. And then when it's starting to get down there. But it should start more aggressively turning in a bit. There we go. All right, that's what we want to see. It's going to dive its way down to 10 to negative 6. And we're going to be good and ready to move on to the next step. Boom, perfect. And then before we leave this one, or actually, just as a quick, just make sure we're not, nothing's messed up before we go plot and stuff. Report definitions, we need the drag coefficient anyway. So right click, new, force report, drag. Let's get the drag coefficient. Let's make sure we're not crazy. Yep, that looks good. It's not 0, but it's pretty darn close. So that is our CD. So we already got one step done. That's part F for the inviscid case. I guess while we're here, I can do the XY plot for the velocity variation and the pressure coefficient variation. So velocity, x velocity, curve length. So this is over the surface of the cylinder. Ball is our cylinder. Perfect. That's how it should look. And then we're going to switch to pressure. We're going to do our pressure coefficient over the curve length, and we're going to plot that. And that also looks pretty good. So we have our pressure coefficient. If you do it over the direction vector, didn't want to do it. There we go. Yeah, it's going to be this here, and then the velocity will be the opposite direction vector. Exactly. So that's our graphs there, but we want it over the curve length because we want it on the surface of the cylinder. So got that. I'm going to save this. Boom. We're done with that. So we have those things for there. Now let's back out of this. And then we're going to open up our results, CFD post, which this one takes a second to open. But once this is open, we're then going to plot the velocity contours, the velocity streamlines, and the pressure contours. Since we already got the drag coefficient, the velocity variation, and the pressure coefficient variation. So once this is open, I'm not really sure why it opened all the way up there. Kind of weird why it opened all the way up there. Oh, we're going to bring it open. Kind of weird, I won't lie. Let me close this real fast. Let's open it again. I hope it doesn't open all the way up there. Oh, it's opening all the way up there again. Interesting. Not really sure why it's doing that. There we go. Got it fixed. Cool. That was weird, but whatever. Back to solving it. So we're looking for a velocity contour. So velocity contour. What we want. We're going to do symmetry 1. We want velocity in the U, or the x direction. And I like a good looking contour, so I'm going to do 1,000. Number of contours. Makes it look you have a lot more colors. So let this load. Of course, the more contours you do, the longer it's going to take to load it. So if you really want just a quick, I think it starts with 11. Oh, looks good. Looks like it should. And we're getting 10.0062, which is pretty darn close to the theoretical, the 2 times on the top, 2 times velocity. So that's good. Now we're going to do our streamlines. So I'm going to hide this velocity contour. I'm going to do the velocity streamline. And I like to do it, we're going to start the streamlines there. We're going to do max number of points. We're going to do vertex. I'm going to do 350. I found this to be good. Oh, sorry, symmetry 1. Don't put inlet, put symmetry 1. Doesn't look right. Because I didn't put a streamline. Don't do what I just did. Not do what I just did. No wonder it didn't look right. I was thinking something else. Okay. Don't do what I just did. 350 points. Now we should get, there we go. There we go. All right, that's looking good. Don't listen to what I just said previously. This looks good. Got our velocity streamline. Now time to do our pressure contour. So we're going to hide this velocity streamline. We're going to do our pressure for perfect. We're going to do symmetry 1, pressure's good. And again, I like having a good image. So we're going to do that. Let this load in. And this is all just for the inviscid case. So here's our pressure contour. So that is everything for our first case. So now we are going to save this. Always save 100%. It really sucks when you lose your files. But I'm going to close this out. And then what I'm going to do is actually grab another fluid flow. And I'm going to actually connect the mesh to this one. So what that's going to do is it's going to transfer the mesh over. You are going to have to click update, let it do its thing. But this should make our lives a lot easier. We don't have to remesh. We don't have to do all that. We just sit here while it updates. So let that do its thing. And then we'll start the viscous laminar case. Okay, cool. So let me label it so I don't get confused. And we're going to label this. Cool. Now we're going to open this setup. I'm actually going to close the previous setup because I do not want ANSYS to crash. So get that closed. I'm also going to close this as well. Reduce the strain on your computer. Let's close that, and then let's close the last one out. Everything's saved, so we're all good. So we're going to, again, double precision, 6 cores, start again. So this one is a little different. You do need, so for it to be laminar, the critical Reynolds number is 500,000. To keep our Reynolds number under 500,000, mine is in the just over 100,000 range that I calculated. Let's let this load in. Always tricks you with letting you try to press the OK when it doesn't let you. Let that do its thing. Okay, cool. So we're going to leave it as viscous K omega. We're going to go to our materials. I calculated using this viscosity 1 for the density. And again, always got to check those reference values because it's not going to change in the reference values, annoying as it is. And my velocity for this case is going to be 2. My velocity is going to be 2. And that is what I calculated to keep my Reynolds number under 500,000. So we're going to do a velocity of 2. I'm going to click apply 100 times to make sure it did it. So let's go through this to make sure I did it correct. We have viscous K omega. We have our air correct. We have all these values correct. We have our velocity correct. Just check those reference values are correct. The methods should be good, coupled, yep, second order. Don't have to change the methods on this one. I'm going to leave the residuals as they are. and you'll see why in a second. But let's just start this run. It takes a second. So let's get this running. And then this case, so this is the laminar. So this should be the biggest wake region. Our CD should be the highest. So we're going to let this in. Yeah, you'll see with this one, these iterations take a lot longer, which is why that simple was so nice. But we're just going to let this run and take its time to get down to 10 to the negative 3. While this is running, I'm actually going to add our next case. So this is the turbulent case. This mesh right over here. I'm not going to update it yet just because this is in the middle of running and this takes all the CPU power. But essentially, we're just going to do the same thing for the laminar that we did with the inviscid and the same thing for the turbulent that we did with the laminar and the inviscid. For the plotting and the velocity variation, the pressure coefficient variation, and the drag coefficient, and the velocity contours and the streamlines, the pressure contours, they're all going to be the same. This one's going to do a bunch of like little waves as it gets down to 10 to the negative 3 with each iteration it dropping a little bit lower. But yeah, once you do the viscous laminar, you've essentially done the viscous turbulent. You just have to switch your Reynolds number to be over 500,000, which mine's like right in the 600,000 range, somewhere between 600 and 700,000. Don't remember off the top of my head. All right, cool. So we're done with this. And then again, I'm just going to do this stuff in here while we can. Report definitions, new, force report, drag. Let's get the drag. This should be significantly higher. And it is 0.564. Looks good. Now let's go to our plots here. Let's XY plot, new. We'll do the pressure one first. Why not? Pressure coefficient, wall. We want this on the curve length. Looks like it should. Now we're going to do the velocity. Velocity. The X velocity. See, that's what's different. It's 0 because of the boundary layer. So this looks good. So let me save this. And let's move on to the next step, which is plotting. Now that that's saved, we can close this one out. And I'm going to open this back up. I'm actually going to update this mesh while we're in here for our next step, the turbulent step. But yeah, this is a lot, big time saver. Being able to, you could also transfer the setup over, but the setup's really easy, so I haven't done that. Cool. So let's go into results and let's do the results for the laminar. And these should be our, like I said, our largest wake region. It's going to have our highest CD value. So we're not going to mess up this time, and we're going to plot the velocity contour, all the contours correctly. Oh, see, already messed up. You can't put velocity. Big mistake. You have to put velocity contour, or you have to name it. Can't name it what it is. Velocity, global symmetry 1,000 contours. I'll show you. Actually, I'll show you. If I did 10 contours, it does it pretty fast, but it looks like garbage. So 100 contours. So it's going to look a lot better, but you still have these like lines, which I'm not a fan of. So I go for the big 1,000. But yeah, you can see this wake region, which we didn't have on the inviscid case because, well, There's no slip, no slip. But with this, looks good. You can see that wake region. We'll compare it with the turbulent case to make sure that turbulent case has a smaller wake region. But yeah, so we got our velocity contour. Now let's do our streamline, not our vector. And we're going to do vertex. We're going to do 350 again because I found that's a good amount. We're going to start from that inlet, and we're going to click apply. We're also going to hide this, and look, looks good. You can see the wake region. Looks perfect. Now we're going to plot those pressure contours. Also can't just call it pressure. Always change it to symmetry. Again, we're doing 1,000. Apply. Let this run, and then we're going to hide this velocity streamline. So obviously it looks weird. Oh, looks good. You can see the low pressure region in the back, the high pressure region in the front. Looks good, looks as it should. We're going to save this, and we're going to move on to our last one, viscous turbulent. I'm going to close this for now, but or just, I guess, memorize in your head what the velocity one looked like. See big wake region, you can see it coming outwards here. You'll see the other one won't do that. But let's get that last one done. Okay, to setup we go. Same thing, we're going to do that double precision, those 6 cores, because I don't like waiting. I mean, some people's CPUs have like 20 cores, and they'll probably be able to do this a lot faster than my computer can, but I don't have a crazy processor, so. All right. And obviously all processors aren't made equal. So if you have an older one, but it has more cores, it might not be as good as a newer one with less cores. All depends. All right, we're in here. We're going to go to our models. It's already SSTK Omega. I don't even have to click on that. Air. The only thing that we're supposed to change is velocity. So that's all I'll be changing. I'm going to go in here and I'm going to change the velocity. I calculated it to be 11. So we're going to change this velocity to 11. We're going to click apply. We're going to go to those reference values and change it to 11. We're also going to snap that density out of it. That's looking good. That's looking really good. Methods, same old method. Monitors, same old residual. I'm going to leave all that, and we're going to run this calculation. This one also is going to take its time because it's not the simple calculation. So we're just going to let this one run. When it's done, we'll do all the same things we just did. The other 2 cases. This is part of the reason why you have to set your convergence so at a lower amount. As you can see, it kind of flat lines for a second, this top turquoise continuity curve, but it's going to start dropping as we go along. Perfect. We're getting close to that 10 to the -3. So we're about to be done. You could set your convergence at a higher number, but again, your values are just not going to be as accurate. And you can see the choppiness at the start versus the more smooth curves at the end. Perfect. Calculation complete. Let's calculate that CD. And let's hope that it's below what the other one is, which should be all inviscid. And it is. That's perfect. Remember, we got like 5.5 something, 0.4 something. So that's looking good. Let's do these XY plots real fast. We'll do the pressure one first. Looking like it should. And then we're going to do our velocity one. And then if you plot the velocity, the direction vector, obviously it's going to be the same. But if you plot the pressure with the direction vector, it's like this. So either plot works. So let's save this. We're almost done to the last part here. Let this save and go to the last part. Cool. So I'm actually just going to X this part out. We don't need it anymore. Literally just on a CFD post. Get to CFD post. Cool. All right, let's do that velocity contour. So this velocity contour should have, like I said, a smaller wake region, as that turbulent air is energizing the boundary layer, causing it to separate later. So we should be seeing that now. And from the looks of it, it is. So I don't know if you remember, but it like on the laminar one, it more bowed out here. But this one, it's kind of staying small. It's not really bowing out. So that boundary layer is separating just a little bit later. And you can see it right here as it starts to separate. But let's continue doing this. So we got the velocity contour. Time to do the streamline. Again, vertex. We're going to start from that inlet. Points. Fly. And then obviously we're going to hide this velocity contour. Looks good. You can see it's a little bit smaller of a wake region here. Harder to see in the streamlines, but definitely in the contour, you can see it. Let's hide this. And finally, contour. Turbulent case. So there you go. That is everything. We did the velocity contours, we did the streamlines, we did the pressure contours for the inviscid, the laminar, the viscous laminar, and the viscous turbulent case. We also plotted the velocity variation on the surface of the cylinder, as well as the pressure coefficient variation on the surface of the cylinder. And then finally, we got the drag coefficients for all three cases. That is it for this project. I hope you guys are able to do it yourself just fine. Thank you for watching.